Welcome back. So last time we talked about vectors. Today we're going to talk about dot product, or as they call it sometimes, inner product of two vectors. The notation, if you have vector u dot vector v, as the way you write it, u dot v. So this is representing an inner product. Later on we will discuss in the next section cross product as well, but at the moment let's focus on dot product. So if given two vector a and b, if they're in 3-dimension, you would have three inputs, a1, a2, and a3. And for b, you'll have three components as well, vector a and b. Then the dot product is defined to be product of corresponding components. So a1 times b1, a2 times b2, and a3 times b3. And the sum of all those three will give you a value. What you need to be careful of is that you multiplying two vectors, and what is the outcome here is a scalar, it's a number. This would be one big difference between the dot product and cross product. Cross product will provide the vector as the result, but dot product will only gives you a number at the end. So you'll have a product of two vector and you'll get a number. There are certain properties to the dot product. If you multiply a vector by itself in terms of dot product, what you get is basically the magnitude squared. You can try to do that, but here, if you remember, the magnitude of a was the square root of a1 squared plus a2 squared plus a3 squared. So if you do a dot a, what you get is a1 times a1 plus a2 times a2 plus a3 times a3. And what this is a1 squared plus a2 squared plus a3 squared. And if you compare this with that, you'll notice that a dot a is basically the magnitude of a squared. So this is not too complicated. And the other property is that if you change the ordering, a dot b or b dot a doesn't really matter. You can interchange this product a1 with b1 or b1 with a1. They are numbers, so the order doesn't matter. And you have the option of distributing. If you have a times two vectors b plus c, you can write them separately, a dot b, then add it with the vector a dot c, so, with the scalar a dot c. These are scalars. If you have a 0 times a is 0, but notice this is product, so which means this 0 is a vector. So it is a, if a is a 3-dimensional vector, you would have 0 as 0, 0, 0. The difference is on the right side, this is just a number. This is just 0. It's not a vector anymore. If you would have said a scalar 0 times a vector a, then what you get is a 3 zeros as the entry. But here, the dot product between these two means you're multiplying the 0 vector, which means all three inputs are 0, as well as a. If you multiply zeros to each component, you'll add them up, you'll still get 0 as a scalar. And if you have a constant k multiplied by the dot product of two vectors, you can multiply the constant by a vector a first, and multiply and do the dot product later on. And the ordering, as again, doesn't matter. This is the same as k times b. This is not dot. Here is dot product with a, if k is a constant. Okay, you cannot write this. This doesn't make sense in terms of a dot b dot c. This does not give you a scalar. This is a vector. I want to make sure that you notice this. This dot product, these two, will give you a scalar. Then if you multiply by a vector, you would get a vector. But in the example, in the property above here, that we've mentioned, this k, I assumed it's a constant. Okay, let's look at this theorem. If theta is an angle between a and b, and let's assume a and b are two vectors, they can be in 2-dimension or 3-dimension, then the dot product of a with b is basically the corresponding product of their magnitude multiplied by the cosine of the angle between. This could be proven basically through a law of sine. So here this vector, if you connect vector A and B, this vector is basically B minus A. Then you can use the law of cosine and you can prove that this is basically true. I don't want to go through the proof, but notice that the dot product could be related toward the magnitude and the angle between two vectors. Which means if you have two orthogonal vectors, what you know is the cosine of the angle between cosine of 90 degrees would be 0. So therefore their dot product would be 0. Okay. And you can use this to find the cosine as well. If you're given two vectors, you can find the cosine of the angle between by just dividing the magnitudes. You can divide both sides by A magnitude B. I'm moving this to the denominator on the other side. And if you want to find the angle theta, then you do a cosine inverse. Then the theta would be basically cosine inverse of whatever A dot B divided by magnitude A magnitude B is. Okay, if the angle is greater than 90, then you would have the option. You cannot go above 180. This is one information that you should know. It should be easy to understand. If you have two vector A and B, the most angle between these two could be is 180. They could be along the same line in the opposite direction. Either this, you cannot consider this outside angle. The angle between them is always less than 180. Nothing too complicated so far. So here is an example. Let's say you're given the magnitudes of two vectors and the angle between them, and they ask you to find out what is A dot B. So how do you find A dot B? You can use the theorem above and say A dot B would be basically the product of the magnitudes. So let me write it: A multiplied by magnitude of B. Let me erase this dot. Cosine of the angle between, which means I have 4 times 3 times cosine of pi third. Pi third is 60 degrees, cosine of 60 degrees is 1/2. So this would be 4 times 3 times 1/2, which is simply 6. And you notice again, two vectors multiply by each other, the result is a constant. Okay, let's look at the next example. You have two vectors, and they ask you to find the angle between those two vectors. Vector A and B are given. So if you want to find the angle, first I'm going to find out what is cosine of theta. I'll say cosine theta would be A dot B divided by magnitude A magnitude B. But what is A dot B? A dot would be multiply the components and add them up. So I'll say 2 times 5 plus 2 times -3 plus -1 times 2. And magnitude of A magnitude of B, magnitude A would be simply square root of 4 plus 4 plus 1. I'm squaring each one of the components of A. That's simply 3. And magnitude of B would be square root of 25 plus 9 plus 4. This is something we have already discussed in the last section. That is 34, 38, I believe. 28, 38, yes, square root of 38. Okay, so what we have is here divide by 3 times square root of 38. Okay, so what is cosine theta? Cosine theta would be, if you multiply the numerator, you'll get 10 minus 6 minus 2, so it would be 2, divided by 3 root 38. And you cannot simplify this more than that. 38 is 2 times 19, so there is no way to simplify. So if you want to find the angle theta, you do cosine inverse of 2 divided by 3 root square root of 38. You can use it to figure out what approximately. I don't have a calculator at the moment, but you could continue and figure out what is that. Okay, so this is how you find the angle between two vectors. So for example, one thing to notice is that if you have vector I and j or k, what do you know about these three vectors is that they are orthogonal to each other. Vector I is simply 1, 0, 0, 0. J is 0, 0, 1. So if you do dot product of these two vectors, sorry, this is k, not k, I and k. So if you do dot product of I and k, what you get is 1 times 0 plus 0 times 0 plus 0 times 1. And what you get is 0. And it tells you that the angle between these two vectors is 90 degrees. They are orthogonal to each other. Otherwise, the dot product would not be 0. The only way that you get the dot product to be 0 is if the cosine of the cosine of the angle between those two vectors is 0, which means either one of the vectors are 0, or if the vectors are non-zero, then the cosine must be 0, which means the angle is 90 degrees between those two. Okay, so here, as I mentioned, if A and B are orthogonal, then A dot B is 0, or if A dot B is 0, then A and B must be orthogonal. This is assuming that A and B are non-zero vectors. And as an example, I did I and J, but here's another example. Can you check if A and B are orthogonal? Then you can do A dot B to figure out what is that. So you get 2i, so the components are 2, 2 and negative 1, 5, negative 4 and 2. You can do 2 times 5 plus 2 times negative 4 plus negative 1 times 2. If you add them up, you'll get 0, which means A is orthogonal to B. This is one way to mention that they are orthogonal. Or you can say the cosine of the angle between is 0, or theta is 90 degrees, doesn't matter. Okay, this was not complicated either. Here is what you should be careful about. Direction angles and direction cosines. You should always make sure that you understand what they're asking, because these two are very similar. What is the direction angle? Direction angle is the angle between the vector A or V. So let's look at this green vector that I drew in 3 dimensions. So let's call it V. The angle between the vector V with each axis. So the vector V, for example, has an angle alpha with the axis X, angle beta with the axis Y, and with the axis Z, we have angle gamma. So this is correspond to the angle created with the x-axis, y-axis, and z-axis. These are called the direction angles. For example, if the vector was picked to be on the x-axis, what do we know is that alpha must be 0, because there is no angle between that vector and the x-axis, and the angle between that vector and y-axis and z-axis, they both should be 90 degrees or pi half. This is as the direction angle. It tells you the angles between each vector with the x, y, and z axis. And what is the direction cosine? The direction cosine is exactly the same thing, but you're calculating the cosine of the angles. Alpha and cosine of beta and cosine of gamma. You might ask why we care about that. Yeah, it's just that there are some certain properties about these cosine angles. One way we can calculate the angles is through what we talked about. If you have the vector I along the x-axis, and I ask you what is the angle between vector I and vector V, you can find that through what we talked about. How do you find the angle between vector I and vector V? the angle between vector I and vector V can follow this, this one. Let me highlight it. Through the cosine inverse, you can find out the angle. We did an example. Instead of A, you have vector V. Instead of B, you have standard vector I. And what does it tell you? It tells you the angle alpha, the angle that you create with the x-axis. So to find cosine of the angle alpha, basically what you need to do is do dot product of A with the angle I, and then divided by the magnitude of A, magnitude of, I forgot to mention this, magnitude of I. But what do we know about vector I? It's a unit vector, right? So if A is the components of A are A1, A2, and A3, and I is 1, 0, 0, what we know is A dot I would be this times 1. The other two would be multiplied by 0 in terms of dot product. So what would be the dot product? Would be A1 times 1, A2 times 0, A3 times 0, add those up. So you'll get simply A1 times A1, which would be A1. So this is the first component of the vector, A1. And the magnitude of I is simply 1. So I can say, okay, the denominator is simply the magnitude of A. So I found out what is cosine alpha. Cosine alpha is the first component divided by the magnitude. Similarly, what would be cosine beta? Is the corresponding y component, which is A2, still divide by the magnitude. This is if you multiply, if you do dot product of A with the j vector. And as well, cosine of gamma could be found by doing A3 divided by the magnitude of A. This is how you find the cosine direction cosines. And if you want to find the angle alpha, beta, and gamma, you just take a cosine inverse. So the cosine inverse of A2 divided by magnitude of A basically tells you the angle beta, for example. Okay, so what we notice is this property. This is a kind of an important property. So if you have two of the angles, you can find out the third angle. If you square these components, if you square that, this one and that one, what you get is A1 squared divided by magnitude of A squared. If you add it to the second, you'll have A2 squared divided by magnitude of A squared plus A3 squared divided by the magnitude of A squared. If you add the numerators, since the denominators are equal to each other, what you get is basically A1 squared plus A2 squared plus A3 squared. That is exactly the same as magnitude squared of A. So this ratio is 1. This is the same as cosine alpha. That is the same as cosine beta. This is the same as cosine gamma, all squared. So you have cosine alpha squared, cosine beta squared, and cosine gamma squared. And if you add those, you'll get 1 as the summation. So if you know two of the angles, finding the third angle would be just using this property. Okay, I already highlighted it. Or you can look at this A vector and say, I can write the A vector in terms of these cosine angles. How do I do that? Again, let's look at this highlighted section. Let me change the highlight to a different color. Sorry, this erasing the highlight is always a problem. A3. Okay, let's pick maybe a light blue. Okay, so if we look at these three, and if you have vector A is basically A1, A2, and A3. If I divide A by its magnitude, I can write it as magnitude A multiplied by, it's not dot product, it's a constant. So, multiply by A1 divided by magnitude A A2 divided by magnitude A, A3 divided by magnitude A. I haven't changed anything about A, I just factored out the magnitude A. The first component now is exactly the same as cosine alpha. Second component, cosine beta. Third component, cosine gamma. So you can find out the cosine of each angle just by factoring out the magnitude, or you can divide A by its magnitude. You can, okay, so if I move this to that denominator of A, what do I get is basically the first component would give you the cosine of angle alpha, cosine of the angle beta would be the second component, and so on. So here's an example A, and they ask you find the cosine, I should have mentioned, find the cosine components, cosine directions, sorry, cosine direction, direction cosine or cosine direction, direction cosine, sorry. The direction cosine. Easy way is first find the magnitude A, would be square root of 1 plus 1 plus 4, so 1 plus 4 plus 1, which is simply 6, square root of 6. So what would be the cosines? I will divide A by its magnitude, so I can say cosine alpha, cosine beta, cosine gamma would be 1 divided by square root of 6, 2 divided by square root of 6, and 1 divided by square root of 6. Right? If they ask you what is alpha, for example, you will say, okay, I take cosine inverse. So cosine inverse of the corresponding angle, corresponding component to the angle alpha, so it would be 1 over square root of 6. Again, you can use a calculator to figure out what is this value. Okay, not super complicated, but you gotta be a bit careful not to make any mistakes. Now let's look at the projection. What is the projection? Projection of a vector onto another vector. So for example, if you have vector B and you're trying to project it onto vector A, what does that mean? So here you have vector B and here's vector A. Projection of vector B onto A is drawing an orthogonal from the terminal state of B onto vector A, and you look at this new vector created from the same initial point up to that end of the projection point. This vector is not specifically exactly in the same direction of A. It could be in the opposite direction depending on the angle. If the angle is greater than 90 degrees, then when you draw the orthogonal, it would be in the opposite direction. So will you have this second picture? You would have this. And the notation for it is, if you project vector A onto B, you can use projection of B onto A to represent it. And what does this represent is that vector, the red vector. But before we find the formula for this projection, let's mention that you can find the magnitude of this vector just by looking at the triangle. If you have this magnitude, which is B, magnitude of B, and if you have the angle theta, and I ask you what is this length, the length should be magnitude B times cosine theta by the trigonometry. So I can basically find the magnitude of this projection. It is magnitude B times cosine theta, and that is what we call the scalar projection, or the component of B along A. The only thing that matters is that if theta is greater than 90, like in this case, if theta is greater than 90 degrees, then what you get is this value becomes negative because cosine becomes negative. So it is basically a signed magnitude. It's either positive or negative depending on angle theta being greater than or less than 90 degrees. So B cosine theta, magnitude of B times cosine theta, gives you that assigned magnitude. That's what we call it scalar projection. So magnitude of b times cosine theta, that is the scalar projection. Another way to write it is by doing a dot b. What you get is magnitude b cosine theta, but we don't need the magnitude a, so we divide it by the magnitude of a. These two are exactly the same thing. These two are equivalent to each other. They are equal. They both give you assigned magnitude value. What is the vector projection now? If I know the length of this vector, I just need to multiply it by a unit vector. What unit vector? Unit vector along A. So I just need to multiply the scalar projection, multiply by a unit vector. So I just need to multiply this. If you multiply by a unit vector along A, and what is that unit vector? Unit vector along A would be A divided by its magnitude. We turn it into a unit vector by doing this. So if you do that, if you multiply it by that, the denominator becomes magnitude squared. And what you have is A dot B divided by the magnitude squared multiplied by A. And that gives you the vector projection of B onto A. This is the vector projection of B onto A. The top one was a scalar projection of B onto A. Okay, by the way, if they change and they say what is the vector projection sorry about the bad handwriting, projection of A onto B, because I've seen students make mistakes through this. You would say a projection of A onto B would be exactly the same as that. A dot B, you change A and B. It's just the order. Instead of A, you have B in the denominator and multiply by B. This is squared. Multiply by B. It's just renaming A with B, B with A. It's the same thing. And I didn't change the order of the numerator because A dot P is the same as A dot B. If you change the ordering, it doesn't really make any difference in the numerator. Okay, so here's an example. Find the scalar and a vector projection of B onto A. So what is the scalar? Scalar projection? Or component projection, sometimes I write it. I should say component B onto A. It would be, did I mention it above here? I should have mentioned here that instead of writing the projection, they write component of B onto A as the scalar projection. So it would be A dot B divided by magnitude of A. It would be A dot B divided by magnitude of A. A dot B, you can calculate that. It would be 1 times negative 2 plus 1 times 3 plus 2 times 1 divided by magnitude A, which is square root of 4 plus 9 plus 1. This is negative 2 and 2 will cancel out, so you'll get 3 divided by square root of 14. This is the scalar projection. This gives you the length of that projection. And now you see that since this is positive, that means the angle between A and B is less than 90 degrees. How about the vector projection? It's very similar. Projection of B onto A would be A dot B divided by A squared times the vector A. You can put the vector arrow above this just to make sure that you're doing it correctly. Okay, so A dot B, we've already calculated that. That was 3. A, magnitude of A, we calculated that was 14. But if you square it, square root of 14, you'll get 14. Multiply by A. What is A? Negative 2, 3, and 1. And what you get is, you can multiply these numbers inside or you can keep it outside. It's up to you. Negative 6 divided by 14 or there is a simplification if you want 9 divided by 14, 1 divided by 14. Sorry, 3 divided by 14. And I found a vector. This vector is in the direction of A, and it's the projection of B onto A. Not too difficult, I hope. Okay, and some of the application of the projection is in physics. You've dealt with work, which is force times displacement. In Calc 1, there was some part that had this work and displacement. The only thing that we noticed that in that time, we assumed that everything was in the same direction. So if you had the force and displacement in the same direction. In force by displacement. There was no changing, there was no angle between the force and the displacement. So if between the force. So for example, if you're pulling something with a certain angle, but the displacement happens on the ground, then what you can say is that the work done is basically the force along that displacement. The force along the displacement would be the force that you put along this direction, which is, in terms of length, it would be magnitude of F times cosine theta. That is the scalar magnitude, scalar projection, and multiply by the distance. If the distance is a vector, then you have to consider the magnitude. That is the work done in this direction. But you can rewrite this in terms of just the dot product. It is F times D, magnitude F magnitude D cosine theta, which is basically saying that the product of the inner product of two vectors. As an example here, a force F, which is a vector, moves a particle from point A to point B. Let's say point A to point B. You can consider this as initial point A and that the terminal point B. Or in this case, I wrote P and Q, it could be A and B. So let me use P and Q. P to Q. And we're going to find out what is the work done along this by doing by having this force onto this particle. So you can find out first the vector D. So what is the vector D? The vector D would be the difference between these 2 points. P2, the terminal minus the initial. So it should be 4 minus 2, which is 2. 6 minus 1, 5, and 2 minus 0, 2. This is the vector D. These are points, by the way. You see parentheses. And then the work done is simply F dot D, which is 3 times 2, 6. 3 times 2 plus 4 times 5 plus 5 times 2. You don't need to draw any pictures. This is fairly easy. This is 20, 30, 36 joule, if you want, as the unit of the work done. Okay, so this is one of the applications, and the most common one actually is the work for the inner product. There are more applications, but you can see maybe more of those examples in textbook and the homeworks. So I'm going to stop at this point. This is the end of 12.3. And next time we will move on to the cross product, which is the product of two vectors, and the outcome would be a vector. So let's stop at this point.